Yesterday we could complete the first module of the course, what basically focused on how to make decisions when there are multiple objectives, there are multiple constraints, and there are multiple stakeholders. What basically we did in that module, initially we discussed about various economic problems that are related to multiple objectives, multiple constraints, multiple stakeholders, and then how to solve some such complex problems by using AI techniques. So there are two components in module 1. One was basically the problems, the situations that we can define in context of economics, and the second part is basically to solve those complex problems. Now in module 2, we are basically focusing on learning from data, and the first component is basically on the time series perspective, basically the forecasting related issues. I'll be getting into that soon, but before that, let me tell you, in second component of this module, we have simple prediction algorithms for numeric and non-numeric data, basically in the context of linear regression and decision trees, which will be basically, the lectures in this component would be delivered by Professor Mitra. What I'll do today, basically, I'll give you an overview of time series forecasting for low, medium, and high frequency data. I'll basically focus on numeric data, and as far as the non-numeric data are concerned, I'll get back to this part, particularly when I deliver the other lecture on discrete choice model. Basically component number 8, the fourth component of this module. Okay, so in today's lecture, I'll be basically focusing on the perspective of time series forecasting. I'll not discuss about how to carry out time series forecasting. That would be dealt by Professor Mitra. I'll be basically giving you the perspective from economics, how to go about basically the alternative scenarios and the underlying issues relating to time series forecasting. Okay, so I'll share this presentation. Is it visible?
Yes, sir.
Okay. So, as you know, a time series has 4 components. There is a trend component. A part of a series is cyclic. Then there may be seasonal component and randomness. Now, to what extent different components are present in a series, that may differ depending on frequency of the data, the particular variable itself, and also depending on the context. Now these 4 components, maybe we can assume them to be additive. They can be in multiplicative form. Some component may be very strong and some others may be having less presence. But broadly we say a time series has four components: the trend component, the cyclical part, seasonal part, and randomness. And in many cases, while analyzing time series data, what we do, sometimes we detrain the series, sometimes we take out the seasonal component, sometimes we take out the randomness, again depending on the objective. Now, there are various situations where we use time series data in economics. I will get back to specific examples. But before that, let me tell you, I think there are some students from economics where we in courses relating to econometrics, we discussed about different types of data, like say cross-sectional data, where basically we have data across individual units at a particular point of time. Then we have time series data, means data for a particular cross-sectional unit, maybe it may be for an economy, for a state, for a sector, over a period of time. And then we also combine the time series and cross-sectional perspective, and we have the panel data. We have certain specific context when we use cross-sectional data. We have also situations where it is very much time specific. And nowadays, in many research, we are using panel data as well. Now let me get back to the specific areas where use of time series data is very, very important. Like say we would like to forecast growth of GDP in next 10 years. Suppose I want to make investment in a particular domain, and how my investment would be successful in respect of paying back the returns. Let us assume that that depends on the growth of the economy. So if the economy grows at a high rate, then this basically gives me an incentive to invest. And in this case, forecasting the growth of GDP would be very, very important. And that basically we do by using time series data. Similarly, when I make investment, if I take loan and invest, rate of interest would be very, very important, because that would decide the cost of investment. And in that case, forecasting rate of interest over a period of time would be quite crucial to decide whether I should make investment in a particular domain, or I should put my money in some other areas, other assets. So if I want to make investment in some other country, exchange rate may also be very, very important. It may be a very important factor to guide whether to make investment or how much to invest in that particular economy. So there are various areas where use of time series data are evident, and forecasting is also a quite integral part of time series analysis in many contexts. But when we use time series data, there are certain aspects that we need to be very, very careful about. One is the frequency of the data. You will see the topic of this module that I'm discussing today that talks about how to forecast using low frequency, medium frequency, high frequency data. Like in many cases, we have daily data, like say stock prices, Sensex. In many cases, say for example, we have medium frequency data like quarterly data, like the rate of interest. In many cases, we may have annual data or yearly data. So we may have high frequency data like stock price, daily data, medium frequency data like say rate of interest, say low frequency data like GDP, yearly data. Of course, we can have quarterly data also on GDP, but again, I'm just giving an example. So frequency of data is an important aspect in time series forecasting. What type of data we are using? Daily data, very high frequency data. There may be day-to-day fluctuations in the data. In many cases, what happens? Daily data are combined into weekly data into monthly data into quarterly data, and quarterly data into annual data. So one important aspect is frequency of data. Then behavior of the time series. How the variable behaves over the period of time. In many cases, we look at the short-run behavior, like the oscillations and all. And in many cases, we look at how the series behaves over a period of time, that is in the long run. And many of you might be knowing that while dealing with time series data, there are certain important analysis that we carry out, like say testing for stationarity, basically to test whether the basic characteristics of the series have changed over the period of time, whether two series are co-integrated. So these are basically various aspects that we discuss in time series econometrics. And these are very important aspects, in fact. We say that simply using time series data without looking at, say for example, stationarity or presence of unit roots, etc., may result in spurious regression. So behavior of the time series is another important aspect that we look at while forecasting. The other one is basically presence of structural breaks. Again, presence of structural break may result in multiple regression lines even with the same set of data set, same data set. So for example, I have data say from 1970-71 till say 2020-21. An important question is whether I should estimate a single regression line to forecast. To decide that, often what we do, we carry out the tests for structural breaks. What may be the possible sources of structural break? Let me just give one example. That is initiation of economic reforms in 1991. So, if the basic functional relationship is, say, for example, y is equal to alpha plus beta x plus u, then there is every possibility that following economic reforms in 1991, the relationship between x and y has changed. This change may be in respect of intercept. This change may be in respect of slope. This change may be in respect of both slope and intercept. So, for example, we may be interested to know how the relationship between savings and income, or say between consumption and income, has changed following economic reforms in 1991. Now, if I have a data set of 40 years, and if there is initiation of economic reforms in 1991, an important question here is whether we should ignore this point and go for estimating a single regression line using the data for all the 41 years, or we should see if this break is significant, means if initiation of economic reforms has caused significant change in the relationship. As I said, it may be in respect of intercept, it may be in respect of slope, it may be in respect of both slope and intercept. If this impact turns out to be statistically significant, then there are basically two possibilities. Either I can go for estimating two separate regression lines, one, say, for example, from 1970-71 till, say, 1990-91, and then other one from 1991-92 till, say, 2020-21. Because the single line will not work here as the relationship has changed. The other possibility is basically to integrate these two lines by using a dummy variable. And often we do that. Dummy variable is basically a binary variable here. What may take value 1 for the post-reform period and 0 for pre-reform period. It can be another way also. And also we may bring in an interaction term, dummy variable, into the continuous variable x. So the equation now may become y is equal to alpha plus beta into x plus gamma into d, means the dummy variable, plus delta into d into x. And basically the beta coefficient is presenting the gamma coefficient is presenting the change in intercept, and the delta coefficient is presenting the change in slope. And depending on the statistical significance of gamma and delta, we decide whether there has been change in respect of slope or intercept, or the changes have taken place in respect of both slope and intercept. What essentially I am trying to say here, recognizing the presence of structural break is another important component, important aspect in time series analysis. Now there are two broad types of time series analysis. In some cases, we try to see the behavior of a particular variable. Say, for example, how GDP has changed over the period of time. So this basically comprises univariate time series analysis, and the other may be multivariate time series analysis, where we may try to look at the relationship between, say, savings and GDP over the period of time. So in time series analysis, we do both univariate analysis as well as multivariate analysis. But another important dimension is basically the dynamic models in economics. Again, this is a very, very important component of econometrics. In econometrics, we discuss some such dynamic models in detail. Here, basically, what we do, we introduce lags. We introduce lags in the variables. These dynamic models may be autoregressive, like YT is a function of xt, xt minus 1, xt minus 2. It may be up to xt minus k. It may be distributed lag model, the example that I gave. And the other one, as I said, it may be autoregressive, like yt as a function of yt minus 1, or say yt minus 2, or say yt minus k. So dynamic models may be autoregressive when we are writing yt as a function of yt minus 1, yt minus 2, yt minus k. And it may be distributed lag models like yt as a function of xt minus 1, xt minus 2, up to xt minus k. And it may be a combination of the two also. So when we specify autoregressive models like yt as a function of yt minus 1, for example, there basically we are recognizing the fact that the current value of a variable is generated from its past value. Right? Say, for example, my current consumption may be influenced by my past consumption. This autoregressive nature of a variable may be, here it is consumption, which may be very, very important. Say, for example, how much profit I would earn from my business in year T may depend on how much profit I earned in year T minus 1. Because there are various arguments. It is possible that I earned more in the last year, and in the process I could expand my business. I could spend more on various strategies, and this actually helped me to earn more in this year. It is also possible that I earned more last year. This encouraged other firms to come into this business. Competition has increased in the market, and my profitability has gone down this year. Both are possible. But what is important here is the profit function here is dynamic and autoregressive. But again, it may have some distributed lag component also. Like my current profit doesn't depend only on my previous profit. It also depends on some other factors, like say how I spent on advertising, on improving technology, in creating distribution network, etc. Similarly, my current consumption may depend on my past consumption, but at the same time, it depends on income, it depends on rate of interest, and the impact of rate of interest, impact of income may not be confined strictly to their current values. Maybe that my current consumption depends on my current income as well as my past income. Maybe it depends on my current rate of interest as well as the past rate of interest. Similarly, profit may depends on how much I'm spending today on advertising and also on advertising in the last year. How much I'm spending on technology development this year as well as how much I had spent last year. Because one is continuity in various factors, that is one part. And second part is basically the non-instantaneous impact of many of the variables. So it may so happen that city is not exactly a function of YT, means consumption in year T is not exactly a function of income in year T, but it may be a function of income in year T minus 1. With a lag. So dynamic models are evident in economics. It may have alternative specifications. As I said, I mean, YT may be explained as a function of XT. YT may be expressed as a function of, say, YT minus 1 and XT. YT may be expressed as a function of YT minus 1, XT minus 1. YT may be expressed as a function of YT minus 1, YT as a function of YT minus 1, YT minus 2, XT minus 1, XT minus 2, XT minus 3, like that. There are alternative criteria of expressing how many lags to be incorporated. What should be the lag length? What should be the exact specification of the model? Sorry. Of course, this should be guided by the underlying theories, but specifying dynamic models is very common in economics, particularly when we are using time series data. And then time series forecasting. Basically using relationships over a period of time and forecasting for the future. Now, as I said, economic forecasting uses historical data and basically we predict for the future. But as I said, frequency of economic time series may be of 3 types broadly. We may have low frequency data like yearly data on GDP, medium frequency data like quarterly data on interest rate, and high frequency data like daily data on stock prices. Now there are alternative uses. I have basically highlighted here 3 scenarios. I'll add a few more when I come back for the other part. Like investors use forecasts to make informed decisions. Well-informed business decisions is very important, particularly for getting the expected returns. Basically, forecasting about different factors, including the market. Like I was talking about, investing on R&D, in-house R&D. We discussed a lot in earlier module that it takes a bit of time to get the outcome in innovation. then we need to apply for the patent. Then patent would be granted, and then this R&D outcome would be commercialized. So by the time all these steps are completed, it may take even a few years, and the market scenario may change. So if that happens, if the market scenario changes, then that innovation outcome may not be that effective. So what basically this forecasting may help the investors to understand how the market may behave, say 10 years or 15 years down the line, and accordingly the investment decisions may be made. Of course, the accuracy of forecasting depends on various factors, like how systematically you use the data, authenticity or correctness of the data, integration of other information, the model that you use in forecasting. Definitely all these are very, very important. But what is very important here for investors is to forecast correctly for the future, so that the investment decisions can be made accordingly. Like here I have given one example, like forecasting exchange rate. Sorry, there is a spelling error. I'll correct it later and I'll send it to you. Forecasting exchange rate just to forecasting exchange rate to decide investment locations. Similarly, the government entities make policy decisions based on certain forecasts, like central bank forecast inflation and output growth to decide monetary policy, particularly when to decide about the rate of interest. Say, for example, economic reforms were initiated in 1991, and suppose the government, after 3 decades of economic reforms now, for example, the government plans to go for another round of reforms. So forecasting of different important macroeconomic variables in particular, like say inflation rate, interest rate, rate of growth of GDP, right, exchange rate, all would be very, very important. The private firms also forecast, say for example, about their sales, to make decision about how much to produce. Now, what happens? There are various approaches to forecasting. I have just highlighted a few here, like say exponential smoothing, where basically we fit suitable curve or line using historical data, and then that line is extended to forecast about the future. Then single equation regression models, basically estimation of appropriate single equation models. Like, as I said, I mean the relationship between, say for example, savings and income. Because from the macroeconomic point of view, how our saving behavior changes Understanding that is very, very important, because it is savings where from we source the capital to make investment. So saving is very, very important for macroeconomic policies as well. So we may estimate the relationship between, say, saving as the dependent variable, and we may have independent variable like income, rate of interest, etc. Again, as I said, many of the saving schemes are having continuity, like we save in every month or in every year. In every year or in every month, we may need to deposit a particular amount of money. So dynamic specification here may be very, very crucial. That's what I was pointing out. It may have an autoregressive component, like saving in year t may be a function of saving in year t minus 1. Saving may be a function of income. Again, income may have instantaneous impact, like saving in year t may be a function of y in year t, it may be a function of y in year t minus 1. Same can be said in respect of rate of interest. Rate of interest again is a very, very important factor. If rate of interest goes down, say for example, we may decide not to save in bank, but to put the money in some other avenues, like in capital market, in various stocks. The other important specification is basically simultaneous equations, where I'll give some examples. After this slide, I'll give you some examples where multiple equations may be very, very important. Particularly when, say for example, y is a function of x, and at the same time x is also a function of y. Like we say, as income increases, savings will also increase, but at the same time, savings may also influence income. More savings means there is more investment. If we assume that there are investment opportunities, and more investment means more income. So there may be bidirectional causal relationships, and in this case, we may go for estimating simultaneous equation regression models. Autoregressive integrated moving average models. This is a part of time series regression or time series econometrics, where basically we analyze probabilistic or stochastic properties of economic time series. And then we also go for estimating vector autoregressive models that are largely in the line of simultaneous equation models, but where the variables are endogenous. So these are some of the perspectives of time series modeling in economics. There are extensive use of time series data in economics, be it farm level data, be it individual stock prices, be it macroeconomic data. We use time series techniques quite extensively in economics. But again, econometric modeling we do, but in this course, the emphasis will be given on some such analysis, including forecasting by using AI techniques. Now, given this, I'll basically show you now some important examples, what will give you the perspective about why some such analysis are very, very important in economics. I just start with one example, like say Cowboy model. It is a very important model in economics. Is the word file visible? Can you see the word file?
No, sir.
Okay, I'm just uploading the word file.
Just the PPT was visible.
Can you see the word file now?
Yes, it is visible.
Okay. Suppose let us start with Cowboy model. See the interesting part here. Here we are saying quantity demanded in year T is a function of price of that year. Okay. And we are assuming that as the price goes up, quantity demanded will go down. So this is the demand function. So we assume both alpha, beta to be positive. But when I specify the supply function, we specify in a different way. Here we assume that quantity supplied is a function of price, but price of not the present year, but the previous year. Because based on previous year, the producer makes the decision, previous year's price, the producer makes the decision how much to be supplied this year. Because producing output and supplying to the market, these processes take a bit of time. So here we are assuming that the impact is not instantaneous. Impact on supply is not instantaneous, whereas impact on price is instantaneous. And in equilibrium, we assume that quantity demanded is equal to quantity supplied. Now you know how to solve some such models, particularly those who have done some course in economics. You might be knowing that this is the demand function, this is the supply function. So we put both demand and supply function in this equilibrium condition, and then we get first order non-homogeneous difference equation like this. And then what we do? For particular solution, we assume that Pt is equal to Pt minus 1 is equal to P bar, and this gives me the particular solution, which is nothing but the equilibrium price, which is equal to alpha plus gamma divided by beta plus delta. So this is equilibrium price. The other component of difference equation solution, as you know, it is basically the complementary part. What basically will show you how the price, because in this equation price is the variable. So what basically we are doing here, combining the demand and supply function, we are basically getting a first order non-homogeneous difference equation for price. This equation can also be expressed as an autoregressive function. You can see I can express here Pt as a function of Pt minus 1. And when I specify this, and when I say that a particular variable is generated from its past values, and if I extend that line in the process, this may help in forecasting. So again, let me get back to this. So for complementary solution, what I'm assuming Pt as a function of xt, and I'm specifying Pt as a into x to the power t. Obviously, Pt minus 1 is equal to then a into x to the power t minus 1. And in complementary solution, that non-homogeneous component will not be there, that constant part will not be there, that will be made 0. So this is how we rewrite, and we get a solution for x. And this is how we specify the time path of price. Particular solution plus complementary solution, and then we put the restriction for the initial year or the value for the initial year. So when t is equal to 0, P naught, that is price of the initial year, is equal to P bar plus A, and this gives me a solution for the constant A, which is equal to P naught minus P bar. And in the process, we are having the time path of price like this or like this. Now, how this time path or this variable will behave over the period of time, that depends on the relative strength, because here we have assumed that both delta and beta are positive. This is what we have assumed here. You can see we have assumed all these coefficients as positive. So given that this delta and beta both are positive, their relative strength will be very, very important. But one thing is very clear, you can see there is a minus sign here, and this essentially suggests that the time path of price will be oscillatory. So there will be fluctuations. Now, whether this fluctuation would be dampening or explosive or regular, that depends on the relative strength of delta and beta. If this ratio is less than 1, then there will be damped oscillations. If it is greater than 1, then there will be explosive oscillations. And if it is equal to 1, then there will be regular oscillations. So there are 3 alternative possibilities here. Anyway, so this is basically, here we are assuming that quantity demanded depends on current price, but quantity supplied depends on previous price. Okay, and in the process we get the time path of price, and the nature here in this particular model, it would be oscillatory, but whether it will be damped oscillations or explosive oscillations or regular oscillations, that depend on value of delta and beta. Then the other example is, say, I assume that quantity demanded is a function of current price, but quantity supplied is a function of expected price. And this expectation is adaptive in nature. That means I have a tendency to correct my previous errors. And this is how the adaptive expectation behavior is specified in economics. I'm not getting into that detail. If you have interest, just you can read some books or some materials on adaptive expectation behavior. But importantly, by using this adaptive expectation behavior, again, we can get the time path of price. Solution approach is the same. I'm not repeating that. The time path of price as this. But again, here we are not sure about the sign of lambda. Unlike the previous case, we are not very sure the sign of lambda. But one thing is clear, given that all these coefficients are positive, lambda cannot be equal to 1, lambda cannot be greater than 1, because all these coefficients are positive. So only possibility is that lambda is less than 1, but it may be negative, it may be positive. Okay, let us see what may be the alternative scenarios. And here we have 5 possibilities. One possibility is lambda is less than 1. And when lambda is less than 1, the time path would be basically converging steadily. That means the price will steadily converge with equilibrium price. Similarly, lambda is equal to 1, the price will be in equilibrium only. The price will always be in equilibrium. And the other 3 situations are lambda is basically you can see these three alternative scenarios what we discussed. Basically, we are bringing here the negative part in the sense that lambda may be negative, and then again we may have three alternative scenarios in respect of different types of oscillations. Again, other possibility is basically inventory adjustment. I'm basically just giving some examples where I'm assuming that quantity demanded depends on current price, quantity supplied also depends on current price, but there may be inventory, means the market may not be necessarily in equilibrium. So either there would be excess supply or there would be excess demand in the market, and depending on that, price may increase or decrease. Here I'm assuming that if there is excess supply, then price will decrease. If there is excess demand, then price will go up. And this sigma here is basically the coefficient of adjustment. And again, in the same way, we can derive the time path. And again, we have 5 alternative possibilities. So here what we are doing, we are having 2 equations, but these 2 equations are combined by using the third equation, and then we are getting a function in respect of, here in this particular case we are getting equations in respect of price, and we are trying to understand their behavior. And depending on their behavior, we can predict for the future. We can forecast, we can use this behavior in the forecasting process. And this is largely what we do in time series econometrics. We try to understand the behavior of the series. Okay. Now I'll show you another example very quickly where we make use of simultaneous equations, and then I'll stop. Here, let us assume that there are 2 sectors in an economy. Input-output model we had discussed. In module 1, I talked about input-output model, but I discussed that in a static framework. And here, I'm discussing in a dynamic context. I'm assuming that there are 2 sectors in an economy, and the output of the 2 sectors are X1 and X2. I'm also assuming that output of one sector, partly it is used for further production in that sector and also for production in other sector. And the rest is used for final demand. So X1t plus 1 is equal to A11 X1t, A12 X2t plus D1t. And you know what is A11, A12, A21 and A22. I am not discussing on that. And there is a process of solving simultaneous difference equations. And this is how we are solving here. I'm not getting into the solution. I will upload these files. You can have a look. Okay, and if you have any question when I come back for further discussion, you can raise this query in that class. So I have added some examples also. And importantly here, when we solve these equations, we get some time paths like this. And these time paths essentially show how the 2 variables xt and yt, or in that particular example what I showed just now, x1 and x2, they will behave over the period of time. Okay, so here we have described the time paths in a discrete fashion by assuming the time frame to be discrete, and that's why we have used difference equations. But again, similar specification we can make by using continuous time frame like this, and again we can solve simultaneous differential equations. Here essentially we get simultaneous differential equations. You can very well see here x1 prime t basically represents the first order derivative, same is for x2, and these equations again can be solved. These simultaneous differential equations can be solved and the time paths can be derived the way it is written here. These are the time paths. Okay, now what this sort of analysis, this sort of dynamic analysis will help you? They will essentially help you to understand the behavior of the series, whether there are temporal fluctuations in the series, whether the fluctuations are decaying over the period of time or they are expanding further, right? Whether there are any breaks in the series. There may be multiple breaks. Let me tell you the time path that I talked about in the example of structural break. I talked about the time path of say 1970-71 till say 2020-21. So if we have a time frame of say 40-41 years, we can have multiple breaks. One may be in the year 1980-81. There was a significant change in industrial policy. Okay, then we may have a break in the year 1991-92. We may have a break in the year 2008-9. So what essentially I'm saying, we may have multiple breaks, but remember breaks are permanent and fluctuations are largely temporal in nature. So understanding both is very, very important for robust forecasting using time series data. So that's all from my side today. I'll again get back to this module. And now if you have any question, you can ask. Else we can stop. Thank you so much. Any question? Priyanshu? Priyanshu?
Yes, sir.
I think you are from economics, right?
Yes.
So I think you can recall?
Yes, I can recall it.
Yeah. Of course, we'll be discussing a bit in detail. So what about others? Yeah, Priyanshu, do you have any question?
No, sir. Nothing.
Sir, please share those math slides also.
Sorry?
Sir, please upload those slides also in
those Word files,
yeah.
No?
Yeah.
Yeah, I'll upload those files because there I have written down, how to solve these simultaneous difference and differential equations. And that would be very, very important component of, basically to understand the time series behavior using both discrete and continuous time frame. And that will also help you to understand the difference between say temporal fluctuations and permanent shocks like the structural breaks. And having robust forecasting requires in-depth understanding of these aspects. So these are basically the theoretical foundations, and context already I have discussed. And then Professor Mitra will be basically talking about the AI part. And when I come back again for other component of this module, I'll discuss with you in detail about the discrete choice part, where I will be basically focusing on qualitative perspective. Okay. I will send it to Ravi Teja. I will send it to you. You can upload it. Okay, these slides as well as the Word files. Do you have any question? Gyanranjan, do you have any question? Is it clear what we discussed?
Yes, sir.
Maybe the solution part you need to go through the Word files, but I'm asking if the basic perspective of this time series forecasting is clear. Basically, what are the major aspects and what are the different areas of time series forecasting in economics, and what are the foundations, and then Professor Mitra will basically talk about the AI part. Okay, so you go through these files, what I upload, and if you have any doubt, you can always write back to me. I don't know when my other lecture would be scheduled in this module. I'll talk to Professor Mitra and I'll get back to you. I may get back to Ravi Teja and he can drop a message, and we'll continue with a portion of this, and we'll bring in some other issues, particularly the discrete choice models. Okay.